let's move on to the next presenter, which will be the paper is Hawkeye, and the presenter is Shichen Wang. He received a BS degree from the Department of Computer Science and Technology in Tsinghua University in 2019, and PhD degree in Tsinghua University in 2025, respectively. He is currently a research engineer with Huawei Technology. His research interests include programmable network, high-performance network, and network systems. Please.
Thank you for introduction. Hello, everyone. I am Geng Yantao from Tsinghua University. Since the authors of this paper regretfully can't attend the conference in person, I will present this paper on their behalf. It's a unique honor to present this work, Hawkeye. This is a joint work between Tsinghua University, Beihang University, InfraWays, and Quancheng Lab. Let's start with the RDMA network. RDMA is becoming a compelling trend in current networks. By bypassing the OS kernel and directly accessing the memory of remote hosts, it delivers exceptional performance. Leveraging its performance advantages, RDMA is now widely deployed in high-performance data center applications. However, in RDMA, network performance anomalies present new complexity. This complexity mainly stems from RDMA's lossless networking mechanisms. To ensure high performance, RDMA employs lossless mechanisms to eliminate packet loss in the network. Take ROCEv2, one of the most representative RDMA protocols, as an example. It implements losslessness using PFC, or hop-by-hop lossless mechanism. When the downstream ingress queue length exceeds a certain threshold, a path frame is sent to halt packet transmission. When the downstream ingress queue length falls below another threshold, a resume frame is sent to resume packet transmission. PFC introduce a series of network performance anomalies. First, the flow contention in the network, such as microbursts or ECMP load imbalancing, leads to queue congestion. In RDMA networks, this may trigger PFC backpressure, resulting in cascading congestion that affects the performance of flows across multiple links. The second MPA is PFC storm. In addition to PFC backpressure caused by network queue contention, programmatic end hosts may continuously inject PFC frames into the network, leading to widespread cascading congestion. For example, malfunctioning NSAs, slow receiver installs. The third one is deadlock. Routing installs, such as routing loops or link failures, may create cyclic buffer dependency in the network. However, existing solutions for root cause diagnostic of such anomalies face challenges in visibility, efficiency, and coverage. First, there's a lack of fine-grained PFC visibility. Host-based approaches can't determine the presence of PFC or identify specific types of PFC anomalies using end-to-end metrics. In-network approach either fail to detect PFC and its propagation causality, or lack sufficiently fine monitoring granularity to capture flow-level performance impacts of PFC. Second, existing solutions can't efficiently and rapidly trace the causality of PFC spreading. For example, for single switch approaches, since the initial root cause of PFC may be multiple hops away, congestion at the current switch can be difficult to associate with the PFC root cause. Third, current diagnostic approaches lack sufficient accuracy. Traditional diagnostic methods typically rely on analyzing flow contention within queues to identify the flow that contributes most to congestion. However, PLC can mislead this diagnostic paradigm. The root cause of PLC congestion affecting F1 is a burst on switch 2. Yet, analyzing switch 1 port 2 on F1's press fails to associate the issue with the actual root cause, since only F1 and F2 are present in this queue. Therefore, we propose the Hawkeye system to accurately and efficiently diagnose performance anomalies in RDMA networks. It first includes a monitoring system that supports packet-level PFC-aware telemetry. Then it has an anomaly-driven telemetry collection mechanism. We use a host-side agent to monitor end-to-end flow performance. When a performance degradation exceeds a threshold, it generates a diagnostic control packet to trigger the diagnostic. This is followed by an in-network telemetry collection procedure, which is capable of inferring PLC causality at line rate. We first present our monitor system. We set a register array to monitor PLC states of each port, so we can check PLC states for every incoming packet. At the flow level, we augment current flow telemetry with PLC imposed packet number to reflect the performance impact on each flow by PLC. We further add a new telemetry granularity, the port level, including PLC imposed packet number at each port and the port queue depth. Then comes the PLC causality recording. Within each switch, we configure a two-dimensional traffic meter to record the traffic volume between ports. With this data structure, after PLC backpressure is triggered, when upstream switch initials PLC traceback, the downstream switch can determine which ports are responsible for the PLC backpressure propagating upstream. For example, if both switch 2 port 3 and switch 2 port 4 are congested, but port 1 has only traffic to port 3 and has no traffic to port 4, then only port 3 has a causal relationship with the PLC on switch 1 port 1, while switch 1 port 4 is unrelated. Next is our anomaly detection and diagnostic trigger process. When a performance degradation is detected, the host-side monitoring agent generates a polling packet to trigger the diagnosis. We chose this host-based approach because it offers the following advantages. First, high coverage and easy to extend. The host-side agent can monitor every flow, and the monitoring metrics are flexible. Second, low overhead and bandwidth. It generates no extra header on normal packets, and only one packet for each anomaly diagnose. The switch that receives the polling packet needs to collect telemetry and send it to the diagnostic server to build the provenance graph. But the question is, to which switch should we send the polling packet to collect their telemetry? First, we should achieve complete coverage. All switches causally related to the anomaly should be covered. This includes, first, the victim flows path, which stores information about flows competing with the victim flows queue. And then we should cover the switches on the PLC path. Only then we trace back to the root cause of the PLC. However, we must also ensure minimal overhead and avoid carrying extra unnecessary switches. We propose a line rate PLC causal inference mechanism that enables the automatic analysis of correlate-related switches on the switches itself. First, we unicast the polling packet along the victim flow's path. When the switch detects that the victim flow is experiencing PSA, it multicasts the packet at the next switch. In addition to forwarding along the victim flow path, the polling packet is multipassed to all PFC-related and congested ports, thus sending it to the downstream switches. Each switch exerts this process until the polling packet covers all relevant switches. To implement this mechanism, we added a flag field in the polling packet header to indicate whether only the victim flow path should be traced, or if PFC should also be traced. In the switch pipeline, the flag and the PFC causality records are matched to exert packet forwarding and flag modification. The switch that receives the polling packet will mirror the polling packet and send it to the CPU, and then forward the original polling packet normally. The CPU will collect telemetry, which ensures that the forwarding of state plane is not blocked. At the same time, the CPU can also perform some pre-processing of the data to reduce the bandwidth overhead, such as filtering out zero values. After collecting telemetry, Hawkeye will build a provenance graph based on wait-for relationships. Take this pre-FC backpressure anomaly as an example. We treat the flows and ports in the network as nodes to build a provenance graph. First, we add port-to-port edges, present the wait-for relationship at the port level caused by PFC spreading. The wait definition describes how badly PI is paused, how badly PJ's congestion impacts PI, and how badly PJ is congested. Then we build flow-to-port edges, which represent that the flow is waiting for the port paused by PFC. Therefore, its definition is paused packet count of FI at PJ. Next, we use port-to-flow edges to represent anomalies caused by flow contention. We use port-to-flow edges caused by flow contention to describe flow contention. We use telemetry to replace the queue, as shown in the figure. F3's packets are waiting for F4 and F5. We can build such a flow level waiting graph and define F3 F4 as the degree to which F3 waits for F4, which is the number of F4's packets already in the queue when F3's packet enters the queue. To represent each flow's contribution to overall queue computation, for flow F, we take the difference between the degree to which other flows wait for it and the degree to which it waits for other flows. A positive value indicates the flow is a contributor to flow contention, while a negative one means that it's the victim of flow contention. Next, we perform a breakdown of anomalies based on the provenance graph. Each anomaly presents its specific provenance graph, and it enables the matching of centers for typical anomalies, and we can diagnose the root cause. We have constructed centers for some typical anomalies, as shown in the slide. We also designed a formal diagnostic algorithm to analyze the characteristics of the provenance graph and match anomaly types. We then set up innovations. We set an NS3 environment and simulate a fault tree topology. We also set a hardware testbed we implement Hawkeye on an internal Intel Provenance switch. In multiple anomaly diagnosing, Hawkeye presents high diagnostic effectiveness with precision exceeding 19% and recall reaching nearly 100%. It also presents high robustness across various monitoring parameters, primarily the diagnosis triggering thresholds and monitoring empirical sites. Besides, Hawkeye also shows low overhead. It presents much low process overhead because it only collects currently relevant telemetry, and it introduces lower bandwidth overhead because it has much lower extra communication. Hawkeye also fits well on current hardware. Its hardware resource usage also scales well and with concurrent flow number. To summarize, in this work, we observe that RDMA network performance anomalies present new complexity, which mainly stem from cascading congestion and caused by PLC, and existing solutions are less effective and efficient. We then propose Hawkeye, an accurate and efficient RDMA diagnostic system. It contains fine-grained PLC well telemetry, fast in-network PLC causality tracing mechanism, prevalence-based diagnostic algorithm. Innovations provides high effectiveness and lower overhead. Thank you for your attention.
Okay, thank you. Any questions from the audience?
Yeah, thank you for the presentation. Two quick ones. First, how the root causing inference scales with number of passes, and have it to kind of send a lot of packets to finally figure out. And the second is the delay to detection. Yeah.
Thank you. I'm sorry. I'm not the authors with this paper. The authors don't attend the conference, so maybe you can question with his email.
Okay, I think we have this. I think we have the same situation with the first paper. Yeah, really, I really hope the next presenter can answer the audience questions. Okay, so.